We have to see.
Thank you.
Yes.
What?
We're rolling tape now? Okay. All right, so last time we were talking about Taylor's theorem, right? Like in one dimension and so forth. And I'm not going to be able to watch these things personally. You guys can watch it, but no way I can watch it.
Can you say observing session?
Observing session.
What's that?
Observing session.
Yeah.
Because that killed me.
That's very difficult.
It was
My
great.
message. Yeah, great for you, but it's right. Anyway, three-dimensional generalization of Taylor's theorem is that if we've got some function in three variables x, y, z, f of x naught already broke. My high-quality chalk already broke. Y naught plus dy, therefore it's not actually high-quality chalk.
Clearly.
Z naught plus dz, so you're at some point x naught, y naught, z naught, and you go to another very nearby point shifted by dx naught, dy naught, dz naught. How different is the function at that point? Then that'll be f of x naught, y naught, z naught. Oh, there's a little mistake in my own notes there. It's supposed to say f of x naught, y naught, z naught. You're evaluating at the original point there, so to speak. Plus, and then it gets really tiresome after a while putting little subscripts that say evaluated at x naught, y naught, and z naught on all partial derivatives. So I'm going to leave those off and just say plus df dx evaluated at that point x naught, y naught, z naught times dx plus df dy plus partial of f with respect to z dz, and then the fun begins, especially if you get to higher order terms. You know, you have to get every possible combination of partial derivatives of the order in question. So we'll do it for second order, and then for third order, we'll just say, you know, you can do that yourself if you really want to. So plus 1 over 2 factorial, second partial of f with respect to x times dx squared, plus, same deals for y and z, naturally. And then, thing with partial derivatives is you have to also throw in all the different mixed partials. But you know that second partial with respect to x and then with respect to y is equal to second partial with respect to y and then to x. And so there's factors of 2 in front of each of these terms because there's 2 terms which are equal to one another. And so you get plus 2 times second partial with respect to x and y times dx dy plus 2 times second partial of f with respect to x and z times dx dz plus 2 times the second partial of f with respect to y and z times dy dz plus dot dot dot. So in other words, the next would be 1 over 3 factorial and every possible third derivative you can get. And gee, there's lots of those. You know, this third partial, you know, d cubed f, d squared x dy, and so on and so forth. So I think I heard her say, get back in the frame. Hey, if he can hear me, it's good enough. Right, Chad? Right, everybody?
Yeah.
There you go. Right. So we'll put it in the parentheses here. All derivatives evaluated at x naught, y naught, z naught. Right, so big mess. And that means to first order, in other words, we only care about terms which are linear in dx, dy, and dz. No powers, no products. So to first order, what we get is that the actual change in f, which is approximately equal to the differential df. So the differential is what I'm actually going to write here. change in f is approximately the differential df, and the differential when you're in multi-variables is defined to be the first order contribution, the first order piece of the Taylor series expansion. So df dx dx plus df dy dy plus df dz dz. But the thing to notice with that is that, well, you could write that as a vector product, as a scalar product of the vector whose components are df dx times x hat plus df dy times y hat plus df dz times z hat dotted into the vector whose components are dx x hat plus dy y hat plus dz z hat. But this beast right here, the one whose components are the partials, is the gradient of f. So this is the gradient of f, grad f. And this beast right here is what we could call, we're going to call dl, the little displacement in 3 dimensions from the initial point x0, y0, z0. So this is the gradient of f dotted into dl. So this is the generalization to multiple dimensions of df is equal to df dx times dx in 1 dimension. Grad f instead of df dx, and the vector dl instead of just the little displacement dx like we have in 1 dimension. Okay. Questions, comments, observations? I don't have to always be in the frame
When you're talking, it would be better.
when I'm talking. Questions, comments, observations?
I hope you were still in the frame before you jumped.
I think Chad has a question.
Oh, Chad, stop asking such stupid questions. Nobody else needs to have that answer. So I'm not going to bother.
It's going to be a great semester.
We're talking to our
should-
imaginary friend.
I think you should just write bigger for Chad and just write like half the board, like one sentence.
Right.
Like when
Yep.
you can't read it.
Right. Or you know what we could do, of course, I shouldn't be saying this here. We could just like have this fake lecture where everything is wrong. Have the real lecture.
Oh no, he's on to us.
I shouldn't have said that. These can be edited, right?
That's if the
Yes,
editor will
but
do
will.
That's
it.
if the editor will do it. Let's see. All right. So if we draw us a pretty picture, x, y, z. So we talk about position vectors. So if you have a point in space, you can specify it by its position vector. So R naught, you have to have an origin, of course. R naught is the vector whose components are x naught, x hat, plus y naught, y hat, plus z naught, z hat. And this could be our little displacement dl. I'm just picking this, you know, it's just for the purposes of the drawing. dl could be any direction you like, any length that you like. Although typically we think of it as being small, it doesn't have to be. But for the differential to be a good approximation to the actual difference in the function, then dl does have to be small. So there's r naught and dl and r naught plus dl. So in other words, these are the 2 points in question: x naught, y naught, z naught, x naught plus dx, y naught plus dy, z naught plus dz. So just to be explicit, I'll say r naught is x naught, x hat plus y naught, y hat plus z naught, z hat is the position vector. So we go. And we know here is that since df is grad f dot dl, and like any self-respecting inner product, or even ones that don't have any self-respect, they have no choice in the matter, then that's equal to the product of the magnitudes, magnitude of the gradient of f times the magnitude of dl times the cosine of the angle between those two vectors, which isn't on my diagram there. In other words, to find the cosine theta there, you draw them tip to tip. So there's my R naught, there's my cute little dl, and there's theta right there. The point is that df is a maximum. The change in f, in other words, that you incur by displacing a little displacement dl, the change in f is a maximum for a given length dl. So you can imagine I start at some point and I make a bunch of little displacements, all of the same length. So that really defines a sphere, if you will, of possibilities. In other words, take any point in space and make all the displacements the same distance from that point, and you're sweeping out the surface of a sphere. df is a maximum for a given length of dl. So I'll put the magnitude sign around that. When theta is equal to 0, right? Because the dot product is as big as it can get when the two vectors involved have 0 angle between them for a given magnitude of those vectors. Or in other words, grand pi conclusion, the gradient of f points in the direction in which f changes most rapidly. Important to understand that concept. The gradient of f points in the direction in which f changes most rapidly. So I start at my point here, imagine going all these different little displacements, and if the displacement is pointed in the same direction that grad f is, then the change in f is as big as it can possibly be. So the gradient of f is a wondrous thing because it tells us the direction in which f is changing most rapidly. Okay, any questions? Any questions? I'm not going to do that every time.
What, you're gonna receive like awkward emails like half an hour apart of questions from him.
That's right, yes. Right. Get this really fancy, we could like edit things in, splice you guys in. Yes, Dr. Carmen, I have a question. I'm glad you asked. I think this is slick
I
production.
should totally put this on the website.
That's right, yes. All right. So along this direction, then you take the magnitude of grad f, you find that that's df divided by the magnitude of dl. Right? In other words, if cosine theta is 1 because theta is 0, then df is the magnitude of grad f times the magnitude of dl. So just divide both sides by the magnitude of dl, and you find that grad f is df over magnitude of dl. Or in other words, this is what we call the directional derivative here. You're just dividing change in the function by a little displacement along some direction. So that's literally just an ordinary one-dimensional derivative along the direction defined by dl there. So we say that the magnitude of grad f is the derivative of f along the direction of grad f. So the magnitude, so the direction of grad f is the direction f is changing most rapidly, and the magnitude of grad f is how fast f is changing in that direction. So the gradient vector contains both bits of information. It points in the direction f is changing most rapidly, so its direction tells you that, and its magnitude tells you just how rapidly f is changing in the direction in which it is changing most rapidly. So the greater the magnitude of the gradient, the faster f is in fact changing in the maximum rate of change direction. And if you look in any other direction, well then what we can say is that now cosine theta isn't necessarily 1. So, yes, can I help you?
No, we're good.
That grad f, magnitude of grad f times the cosine of theta, in that case will be df divided by the magnitude of dl. In other words, that grad f cosine theta is the directional derivative in whatever direction you're pointing in. Whatever direction you move, grad f cosine theta is the directional derivative in that direction. So fancy multivariable calculus language, if you parameterize the curve with its arc length, then you can find the derivative of a function with respect to that parameter, and that's what the directional derivative is. So a mathematician would want to be fancier and talk about parameterization of the curve, but we're not going to be quite that fancy here. Okay? Questions? No. All right, and always remember that a perfectly good question is, what the hell are you talking about? You know, sometimes you don't know what to ask, so I'm hoping this is not the case here. But whenever you don't know what to ask, there's probably somebody who doesn't know either, and then you're a hero because you had the guts to actually ask it, and you were just saying, they're going to think I'm stupid if I ask what it is, you know, so. Okay, and I wield the magic eraser. All right. Of course I can wield the magic eraser. It's all in your notes, right?
I'm seriously like paying attention for anything that we say different, so I can like read what
Oh, cool. That's actually kind of good. Yeah. See, because then that's forcing you to just be riveted to it.
That's right.
Yeah. Ah.
That was clearly my intention.
Yeah. Okay, we have to stop the tape recording.
No, everything is on the tape.
Everything is on the tape. Wow.
We want Chad to have the full
The
experience.
full experience. Yes. All right. Level surfaces. i.e. contour plot techniques. Right, so it's a little hard to draw level surfaces in 3 dimensions because, well, you know, it's like this, and so you can visualize them, but they're kind of tough to draw. So we'll just draw us a picture here. Oh, another little thing in my notes there, Steph. I said F, and that's supposed to be a Y on that axis there. There's my X and Y axes, and let's say I've got some function of X and Y. So if you were to plot it, it would be a surface. You know, the Z direction is out of the board here, so it would be a surface that could go above and below the plane of the blackboard here. So you could think of it, you know, like it could be the plot of elevation of a hill or something like that. F of X and Y could be altitude as a function of X and Y. And so you could take slices parallel to the XY plane, and then you'd be cutting the hill into slices that all have exactly the same altitude as one another, the same height above the XY plane. And so you get what we call a contour plot. And so it might look something like this. Oh, just for variety, it looks different than the one I drew in the notes there. But I don't think you need to put that in the margin. Okay, and people tend to put little pluses for there's the top of the hill right there. And of course, this could extend as well. And the point I wish to make is that at every location, grad f is going to be perpendicular to the level surfaces of f. The reason being that if you make a displacement along the level surface, so if dl is along a level surface, actually we'll say is along the level surface through a given point, through the point in question, we'll even say. Any point could be the point in question here. Then what should df be for that displacement dl? It should be 0, because the function is supposed to not be changing. Now, delta f might actually not be quite 0, because remember, this is a first order approximation, but remember too that if we do the calculus thing, and we're thinking like, okay, if I take the limit, if I go to the limit as the length of dl goes to 0, then df becomes a better and better approximation to delta f. And so df should equal 0 in that case. You're on a level surface. Those are surfaces where the function has a constant value, and therefore the change of the value of the function as you go from point to point along a level surface by definition is equal to 0. And so what that means is that theta must be 90 degrees. The angle between the gradient of f and dl must be 90 degrees. Since cosine 90 is what gives you 0 for the change there. Or in other words, grad f is perpendicular to dl. And that's, I like to use that symbol for is perpendicular to. So grad f is perpendicular to dl, or in other words, grad f is everywhere perpendicular to the level surfaces. And the magnitude of grad f is inversely proportional to the spacing between the level surfaces. In fact, in a really sophisticated treatment of vector analysis, you actually start with gradients. You define the gradient of a function to be what's called a one form that I mentioned before, and then what we think of as ordinary vectors are defined as linear maps from one forms into numbers, and you get that via basically taking dot product of gradient with the displacement vector is the change in the function, and the change in the function is the number into which the one form is mapping the vector. Man, I wish we could just do a course in that, but oh well, darn. Anyway, so why is that true? Why should it be that the bigger the gradient is, the smaller should be the spacing between the level curves? So if grad f is large, the level curves are close together. Why? Yes?
Just the, if grad f is, if you're talking about a hill, if grad f is large, then it means that altitude is very changing very quickly.
That's exactly right, yes. If grad f is large, right, grad f is the directional derivative, its magnitude is the directional derivative. So if grad f is large, the hill is steep. the altitude is changing rapidly with distance. If distance along the x and y direction, or whatever direction you're displacing in the xy plane. If the hill is steep, that's when the level surfaces are going to be close together. You don't have to walk very far horizontally to go a large distance vertically, is the interpretation of that. So, so the closer the level surfaces are to one another, the longer the arrow you would draw for head F in that case. Okay, questions? All right then, so we've been having magnificent fun with derivatives. Right, everyone? Magnificent fun? Oh, come on.
That was great.
No, that's it. I'm dejected now. See what I
Turn off
have
the
to put
tape.
up with.
Turn off the tape, we're done.
Turn off the tape, that's right, you're done.
All
right.
Yes.
Yes, right.
We should have a party every day just so Chad is jealous.
Just so Chad is jealous, that's right, yes.
Well, I do the music now.
It's not what I meant.
Because you.
I was
Not drugs.
What was that? It looked like he was doing drugs.
That's all right.
I'm blowing a party.
What did he say?
Okay, so line integrals. So, we've got some point that we start off with, specified by position vector A, so that's our initial point in space. And we're going to end up at some final point specified by position vector B. So A and B are my 2 points. And I'm going to go traipsing along some curve between those 2 points. And what I do is I then imagine breaking the path into a bunch of little displacement vectors, a bunch of little DLs along the path. And in the usual calculus way, I say I'm going to make a sum that I take into a limit where all the little displacements keep getting smaller and smaller. So the number of little displacements I take goes to infinity, while each displacement itself gets tinier and tinier and tinier. So what this is supposed to be is a whole bunch of little DLs along the path, little displacements that I'm going to let get infinitely small so that there's an infinite number of them. And in that limit, I've traced a nice smooth curve between the 2 points. And suppose that I have some vector field. When we talk about a vector field, what we mean is just that we've got a function whose value is a vector at every point in space. And so, for example, you've met vector fields before. What's a vector field you've talked about? What's this course about?
Electric field.
Yeah, electric fields, magnetic fields. The electric field is a vector field. Yes.
We are so,
I know.
We're on top of things.
That's right. Yeah.
almost said it, but then I said I'm wrong.
Yeah, Chad.
No,
We're
right.
giving Chad a chance to answer.
We're giving Chad a chance to answer. That's right. That's right, Chad. Yes, vector field. No, Chad, wrong. Puppies are not an example.
Come on.
Okay, so
I can't wait till I hear his comments after this. It's gonna be like, you guys are crazy.
he's just going to quit his other class and just start coming to this.
Or wouldn't it be funny if like, he comes to talk to them and he's like, oh yeah, that was totally, it was really nice to watch that, and then he clearly has no
You
comment.
know he didn't watch
Obviously
it
he didn't
yet.
watch it.
Yeah, that's right, yes. We can put little cues in there.
You should throw in a bonus word for him.
Yeah, the bonus word for today is puppy. Yes. So, anyway, so the electric field is an example of a vector field defined at every point in space. Magnetic fields, we'll just be generic and call our vector field V. So if we have an expression of the form, we're going to go from A to B along some path. So we could say here's the path P, and we put a little subscript on our integral to say it's along that particular path. Note the step. I don't have that on the notes.
I was just going to say.
Yes. If we take v dot dl, that integral along that path is what we mean by the line integral. And you know, just like in one-dimensional calculus, one variable calculus, you talk about a Riemann sum of f times delta x, and you add it all up between a and b and let delta x go to 0, so it becomes the integral of f dx. Same deal here. This is thought of as a sum of v dot dl plus v dot dl plus v dot dl at every point along the path in the limit that all little dl's go to 0 length. So, in other words, what this is saying is add up v dot dl along the path in the limit that all the dl's go to 0. So our v here is a function of x, y, and z. In other words, each point in space, there's a certain value of the vector v at that point in space. So it's a vector function of position. What is an example that you've met before, without looking at your notes? You already looked. Okay, you can't answer that. What's an example you've seen before of something like this in mechanics? Yeah.
I lost.
You're lost, huh? Yeah, just hopeless. Right? Yeah. That's right,
Yes,
Chad.
Chad.
Work is in fact an example. It's much better. I feel much better. Help your answer does. Okay. So, an example that you're very familiar with, I hope, from your days of trees, the days in the forest, as it were, is.
I'm telling you, we said that.
That's fine.
There's not me.
That's right.
Yay.
You could find f dot dl, force dot displacement along some path, and that would be the work done between points A and B. Is that what you were going to?
Right.
And in fact, we'll come back to that because we've got the beloved work energy theorem, which says that the work done is equal to the change in V.
That's right, Chad.
No, Chad is holding off because he wants somebody else to answer.
What did you just say?
The work energy theorem says that the work done on a particle is equal to the change in its, which kind of energy? Kinetic energy. No, not potential. Kinetic energy. Right. The work done is minus the change in the potential energy. So we define the potential energy to be minus the work integral. Change in the potential energy minus the work integral, and that's why energy conservation works out. Because as long as that's a well-defined function. But well, that's what we're getting to here. So, in general, it matters how you go between A and B. If I take this path, I might get a different result than if I take some other path. So in general, the integrals, line integrals, are path dependent. But not always. There are some types of vector fields for which the line integral is path independent. If a force has the property that the work it does is independent of how you go between the 2 points, what kind of force is that? It's a conservative force, yes. A force that votes Republican is one that is independent of how you go between the 2 points. Independent, that's right. Well, yeah, so
Can't
maybe.
be conservative.
Right, they're libertarian somehow. But so there's a tragic misnomer to it. Okay. Anyway, So those are special forces. They're special. Conservative forces, conservative. Actually, I think we really only talk about conservative forces, so I will state that. We don't really talk about it in general. Conservative forces have F dot dl independent of path. And in general, we talk about vector fields that have that property, that the line integral is independent of path. And that's why I say in the notes, in particular, a force field with this property is called conservative force. And note that since df is grad f dot dl, that if we find the line integral of a gradient, so we can have some scalar function, and its gradient at every point is a vector field. That's a perfectly well-defined vector field that you can get from a scalar function. If we integrate the gradient of some scalar function between 2 points along some path, well, for each little displacement, grad f dot dl is just the little change in f that occurs for the function for that little displacement dl. So I'm adding up all the little changes in f between a and b, and well, that's just then going to be the final value minus the initial value. F evaluated at b minus f evaluated at a. That's no more than saying that, suppose that we're monetizing it, and every time you make a little displacement, you either have to pay a little money or get paid a little money. So your bank account is changing by a little amount every time you make a little displacement. Well, if you did that, then the total change in your bank account, in other words, the final amount of money you had minus the initial amount of money you had, would be the sum of all the little changes in your bank account along the way. So it doesn't matter if it's a bank account or just some scalar function, same deal. So this has to be independent of path. The details could certainly be different. The exact deposits and withdrawals to your scalar function account that you made along the way. But since the scalar function is well defined at every point, there is some final value of the scalar function and some initial value of the scalar function at points A and B. And this makes no reference at all to the path you went between them. So the change in the function, being the integral there, says that it's independent of the path. Since the change in the function is equal to the line integral, it can't possibly matter how you went between those 2 points. Does that make sense or not? Questions about that? It's an important point. And I'm not seeing the kind of general happiness that I'd like to see. Yes?
Okay, this is kind of a stupid question, but so we just got done saying in general different paths yield different results.
That's right.
You're saying that if it's a conservative force?
For forces, it's called conservative,
Okay.
if this is the
So
case.
you would need to know whether or not it was conservative before you just treated it like this?
Well,
Or would you-
okay. What I'm saying here is that suppose the vector field that we're integrating happens to be the gradient of some scalar. So I could define some scalar function and take its gradient, and that's a vector that I've generated at every point in space. Okay? Then if I integrate grad f, that will be an example of a vector field which has the property that the line integral doesn't depend on which path you took. So gradients are examples of vector fields which have this path independence of their line integral. And in fact, it goes both ways, it turns out, that if you have a vector field whose line integral is independent of path, then it's possible to write that vector field as the gradient of some scalar function.
So you're saying, like, in general, just line integrals are path independent, but when,
No, line integrals are path
I'm
dependent
sorry,
in
path
general.
dependent.
Right.
But then since we're talking about like the grad f and since it has the scalar, you know, derivative and stuff, in our case it's independent.
Yeah, this for grad f, it's going to be independent of path because every little grad f.dl you make is a little change in f. And you're just adding up all the little changes in the value of the function. And if you add up all the little changes in the value of the function, it has to be true that when you're done, you get the final value of the function minus the initial value of the function. After all, what would it mean to add up all the changes if that wasn't the case? So since we have a scalar involved here, and a scalar function takes every point in space and maps it to some value, namely f of that function, then for a gradient, its line integral has to be path independent. And as I said, it actually works both ways. Any vector field whose line integral is path independent can be expressed as the gradient of some scalar function. So one implies the other in a virtuous circle of harmonious happiness. Yes, and being in that harmony. Can you think of an example of a vector field which would not be, which would have, what am I trying to, well, I'll hold off on that, okay? Because I'll point something out first else, and then it'll be maybe more obvious what a counterexample would be. But suppose that you reverse the direction along which you've traced a line integral, okay? So here's my point A, here's my point B. So notice I'm labeling points with vectors, and what it's understood when I do that is that I'm referring to the position vector that connects the origin to the point in question. So here's my point A and my point B, and I trace some path between them, and generally we just draw an arrow, a single arrow on the path to indicate which direction we've moved along the path between A and B. Well, suppose that having made this journey, we decide that home was actually not so bad after all, and we actually draw a duplicate path. Okay, those are supposed to be identical to one another. But I trace it along the other direction. I trace it backwards. If we reverse the direction of a line integral, the sign flips. In other words, the integral from B to A of d dot dl is equal to minus the integral from A to B of b dot dl along some particular path. This is always true. If I flip the direction in which I traverse a line integral, but I keep the path the same, then the sign of the line integral flips. Why? Why should that be true? Yes?
You would go, like, if you go back to B minus F, it's B F minus F.
That'd be one way to look at it, except that, and so for a gradient, you're certainly right. For a gradient, that would suffice. That would be a perfectly legitimate argument. What if it's not a gradient? What if it's just some general vector field which cannot be expressed as a gradient? Yes?
Or in one of the other definitions, like you use it as the cosine of theta.
Mm-hmm.
You know all your thetas are going to be 180 degrees opposite.
Right.
Which flips the sign.
Right, that's exactly right. In other words, pick any little displacement along our path here. If you go in this direction, your dl looks like this. And so here, you got v dot dl is a little contribution to the line integral at that point. Now, if I flip the direction so that dl has become minus dl, this v dot dl is going to be, I mean, maybe the best way to write it would say, here we've got v dot minus dl along this path here. Every dl becomes a minus dl along the other path, and so therefore you flip the sign. When you take a dot b and a dot minus b, that flips the sign. Or another way to put it is that the angle has become 180 degrees apart from what it was before, because your vector has become your dl is 180 degrees away from what it was before. So you've added 180 degrees to all the angles, if you will, and so that flips the sign of the cosine when you add 180 degrees to it. So all the little dl's flip signs, or change direction. All the little dl's are now in the opposite direction. So each little d dot dl changes sign. So flipping the direction in which you traverse a line integral flips the sign of the line integral. This shouldn't be a shock, because in one dimension, well, what happens, if I go from b to a of f of x dx versus a to b of f of x dx, what happens? Changes the sign, right? So this is just very similar to the one-dimensional example. Changing the order you do it changes the sign. If you go backwards, it changes the sign. Okay, break time.
Wait,
So beautiful.
Give me a cue.
Q.
Okay, so because of the fact that we've reversed the direction, the line integral changes sign. Now consider the situation. Suppose you go on a closed path between A and B. In other words, suppose I go, here's A, here's B, and I go like this, let's say, okay? And then I trace back home along some different path, all right? Now the point is that if the line integral is independent of path, it's path independent,
Well,
what? Yeah, because I guess it's really a compound adjective, right? So if it's a path-independent line integral, then what we'll find then is that the line integral around that closed path, so we use a little circle to indicate that it's a closed path, which will be the line integral from A to B plus the line integral from B to A. So we can say, like, this is path 1 and this is path 2, and the whole thing together is the whole path. Then our line integral around the whole path, the circle means we've gone around a closed path. Line integral from A to B along path P1 plus line integral from B to A along path P2. So that is going to be equal to, well, by path independence, it didn't matter that I went along path 2. It'd be the same thing as if I'd just gone back along path 1. But then these two things are equal and opposite to one another, and so that adds up to 0.
Oh, Marvin.
Okay? So those two statements are equivalent, in other words. The line integral is path independent, or the line integral around any closed path is 0. Those are equivalent statements. Okay? Happiness and joy. Any questions? So, remember, you must have learned from Dr. Trees that with conservative forces, you can either say that the work done is independent of the path that you take, or the work done around a closed path is equal to 0. That's the no. So in general, a vector field can have that property. It doesn't have to be a force. Forces is one example of something, of a vector field. All right. So can you think of an example? Because I want to impress on you that vector fields that have this property of path independence are special. It's not just any old vector field can do that. So can you think of a counterexample? What's an example of a vector field where the line integral around a closed path would not be equal to 0? How might you draw one? A vector field whose line integral around a closed path is not 0. I suppose, for example, that my closed path is a circle. How might I come up with a vector field such that when I integrate around that circle, I am not going to get 0. When I get back to the end, I've gotten something finite, not 0. I get 0 is finite. What does the magnetic field look like around a wire? Yeah, so I got a straight wire, current flowing down that wire. What do the magnetic field lights look like? No, not out. They go around it, right? They go around the wire, okay? So, in other words, the magnetic field vector, oops, I can draw this, would be everywhere tangent to this circle. Suppose I've got this wire and there's a current flowing through the wire. The magnetic field, you may recall, is such that the magnetic field lines make circles around the wire if you've got a long straight wire, which means the magnetic field vector itself is tangent to a circle at every point around the wire. And then I could talk about finding the line integral of B dot dl around that circle. Well, all the B dot dl's are, if all the dl's had the same magnitude, they don't have to, you can break the path up with different length dl's, but suppose you break it up with all the same length dl's, all the B dot dl's would be exactly equal to one another in that case. So, are there any negative contributions? If this is B and I trace the path in the direction that B is pointing at each location, do I ever get any negative contributions for B dot dl? No, I don't. So if I go all the way around the path, there's no way it could end up 0 because every contribution is positive in that case. And so I suspect you've already used that idea before, where suppose that this is a circle of radius r. Okay, what would the integral, the line integral B dot dl be around that path? Well, okay, so B dot dl is equal to the magnitude of B times the magnitude of dl times the cosine of the angle between B and dl. And what's the angle between B and dl at every point? 0, because dl is tangent to the circle and B is tangent to the circle. So B dot dl is equal to the magnitude of B times the magnitude of dl for every little B dot dl. So we're adding up magnitude of B magnitude of dl. Magnitude of b, it turns out, I mean, we're kind of jumping ahead here, but the magnitude of b is everywhere constant. We just assume that here. So it pulls out of the integral. So you're adding up all the little lengths of the dl's around the whole path, which adds up to what? 2 pi r. That's just the circumference of the circle. So you get 2 pi r times b, where we just use the notation that b means the magnitude of b when you don't draw the little arrow on top of it. So there's an example of a line integral around a closed path that isn't going to add up to 0. And in general, the magnetic field has that property. The line integral of the magnetic field doesn't add up to 0 around a closed path. And in fact, we'll eventually talk about Ampere's law, where we'll say that, oh yeah, and that's equal to mu naught times the current enclosed. Remember that? Okay? So, fun with line integrals. We're going to have lots of fun with line integrals, but we don't want to oversaturate ourselves with line integral fun, so let's go to flux integral fun instead. All right. It's time to talk about flux and divergence. And this is a case where I have to say that you know, your book comes highly recommended, seems like a very good book, but I think he drops the ball when he talks about divergence and curl, because he waves his hands a lot, doesn't derive their expressions really particularly, he just says what they mean without really convincing you that that's what they mean. So I'm going to try to convince you that that is what they mean. And along those lines, he said, running out of the room, talk amongst yourselves.
Hey, Chet, how's it going? And then he ran back to the room, realizing the book he was going to show you is sitting on his board. And he's not seeing it here. It's that Berkeley Physics Volume 2 book. Yeah, that's at home, right? So anyway, next time I'll show you the book. It's a nice book.
You sure got out in the end, that was
Super
fun.
Dr.
What's that? Great. And so, you can even do things like, you know, say like, hi, Chad. Anyway, the author of the book is Purcell, and it's a very nice book that I'm being inspired by as I explain what curl and divergence are. And in particular, that's where I learned how to derive what curl and divergence are.
You should
Back when I was an
letter.
undergraduate. I'm sorry?
You should write Griffiths an angry letter.
No, I won't do that. Seems like a nice guy.
Oh, that's definitely not really good.
Yes, that's right.
You wrote a form.
No, I haven't heard it.
Flux of B, flux of a vector field B. And be sure to understand, by the way, that that's really what the word field means technically. Field is something that assigns a value at every point in space. So you got the electric field means that there's an electric vector at every point in space. That's what the field part of it means. The flux of a vector field V through a surface S is, so we put a little subscript S to mean it's through a particular surface. The integral of V dot dA, or another way to write it is the integral of V dot n hat dA, where the n hat is the outward unit normal to the surface.
at each point. So n hat is different from point to point, but every point has a little outward unit normal vector associated. So we could have some surface and Steph, attention. In my notes, it's supposed, and everybody else too, this is supposed to say bounding curve, not bounding surface. So in other words, the idea is, think of this as like I'm blowing a soap bubble. And so this is the loop that the soap was on, and I'm going, whoo, and then a surface sticks out around the loop. So that's the idea here. Here's an edge to the surface, in other words. This is the edge of the surface, and here's the surface itself. This is an open surface that I've drawn, in other words. It's not broken up into an inside and an outside. It doesn't enclose a volume. And here's a cute little patch of area. So that's a little dA, a little patch of area on the surface. And n hat is a unit vector which is perpendicular to the surface at that little patch. So, this is one of these deals where you're letting everything shrink to 0. So you imagine dA is going to shrink to 0, so n hat's in the middle of dA, pointing perpendicular to the surface. So dA, the vector, is defined to be n hat times dA, the area of the patch. So the patch area is a little vector whose length is equal to the area of that patch of surface, and which points in the outward direction. Okay, question, any source of possible ambiguity here? Yeah, what does outward mean? For an open surface, it's completely arbitrary which direction you pick to be outward. And you just have to be consistent. In other words, it's really an issue for topology to define this, but outward, I could take outward to mean what I've drawn here, and then every n hat would have to be the one that corresponds to that same sense of outward. But you could just as well take outwards to be where it'd be pointing 180 degrees away from that. For an open surface, outward is completely arbitrary. It's up to you which direction you want to call outward. But for a closed surface, one which actually has a volume enclosed within it, then outward is unambiguous. Inwards and outwards are perfectly unambiguous for a closed surface, and outward really means pointing away from the enclosed volume, pointing towards the outside of the surface as opposed to the inside. Now, you guys have met fluxes before. In what context? What vector have you often taken fluxes for? Magnetic, yeah, you've certainly done that. What other vector have you often taken fluxes for? Electric field too, right? Remember Gauss's law, the flux of the electric field through any closed surface is equal to charge enclosed divided by, actually that depends on the set of units involved, but epsilon naught if you're using MKS units. Q enclosed over epsilon naught is the flux of the electric field through any closed surface. For the magnetic field, the flux through any closed surface is equal to 0. Yeah, magnetic field is fluxless as for any closed surface. I mean, certainly open surfaces can have flux of magnetic field. Talk about magnetic induction, Faraday's law, that relates the flux of the magnetic field through a surface the rate of change of the flux of the magnetic field through a surface to the line integral of the electric field around the bounding curve of that surface. As we'll see, in essence, of Faraday's law. Anyway, we'll get to that later. So, just as we had this fundamental theorem for gradients, and I didn't actually put it in those terms, but I probably should mention that here. talk about the fundamental theorem of calculus. In one dimension, what's the fundamental theorem of calculus say? Yes?
Integral of like x dx equals x minus x.
Yeah, or careful, the integral of, yeah, you're on the right tracks, but yeah, it's the one that relates derivatives and integrals to one another, right? It's the one that says that the integral from a to b of the derivative of some function is equal to the function itself evaluated at the endpoints and subtracted. The fundamental theorem of calculus is the one that says the integral from a to b of df dx dx is f of b minus f of a. Now sometimes that is put in terms of the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where f is equal to the derivative of capital F. In other words, it's the idea that when you take an integral, you use the antiderivative when you're evaluating the integral. But if you've already written it as the integral of a derivative, well, then the antiderivative is the function itself. So that's the way I've chosen to write it there. That's the fundamental theorem of calculus in one dimension. And be sure you understand that really there's nothing mysterious about that. In other words, be sure you understand that df dx times dx is just df. It's just the little change in f. And if you add up the little change in the value of the function between the points, you're going to get the difference between the value of the function at the right endpoint or whatever and the value of the function at the other endpoint. You should have a good intuitive understanding of the fundamental theorem of calculus. It's not mysterious. It took a genius to figure it out, but once Newton did that for us, it's not mysterious, ultimately, why that is true. Multi-dimensional version, is what? We've already written it, so what's the multi-dimensional generalization of this that we've already written? The grad f one, right. The multi-dimensional version is that the integral from a to b, grad f dot dl, is equal to f of b minus f of a, and that works in however many dimensions you like. That works in 473 dimensions, or whatever. It doesn't matter. So in other words, we've got a theorem which relates gradients and line integrals to one another, and we're going to talk about a similar theorem which relates a derivative to an integral. But instead of relating the gradient derivative to a line integral, we're going to relate a different kind of derivative, the divergence of a function, of a vector function, to the surface integral of that vector function. So we're kind of hopping up here. It's another relation between a vector derivative and a vector integral that we're going to come up with here. It's called the divergence theorem. And this is probably the first truly new thing that because you guys have taken multivariables. You guys have seen the divergence theorem, right? You know that the integral of div f dv is equal to the surface integral of b dot dA. Does that sound familiar from multivariable? You're looking like, yeah, I probably knew that once. A few years ago, okay. This is something you're going to relearn from multivariable calculus. And I don't know how they presented it then, but personally, I didn't learn this in multivariable calculus. I learned it in physics. And then in multivariable calculus, I said, oh yeah, I already know that. And by the way I learned it actually made sense. So I'm hoping that this will make sense as we do this here. So this is very much worth understanding how this goes. So, we're going to define the divergence of a vector field V. So V, again, is my generic name for a vector field at a given point
div v, so div stands for divergence here, and then later on we'll use a different notation, del dot v, but we won't do that until we justify it. Div v, by definition, is the limit as d tau goes to 0 of the integral of v, the flux of v through some surface surrounding the point. So surface integral of v dot dA, flux through that surface, and I'm going to put a little circle around it. I didn't do that in the notes either, I meant to, because it's an integral through a closed surface surrounding the point in question, divided by d tau, where d tau is the volume enclosed by S. It's a pretty common notation to say that volume is tau. So d tau is a little element of volume. So here's a point, and we surround that point with some little surface, and there's a vector field defined in space here. So we can talk about the flux of that vector field through this surface, add up all the little v dot dAs at each point on the surface, and then we divide it by the volume enclosed by the surface, d tau. And if this is well defined, if this limit exists, we call that the divergence of v. Is the divergence of v a vector or a scalar? It's a scalar, right? Because the flux is a scalar. Why is the flux a scalar? Because it's a dot product, right? It's a sum of a bunch of dot products. You're adding up a bunch of v dot dAs. So the flux is in fact a scalar. So the divergence is a scalar related to this vector. And we'll see that it in fact is a derivative, which kind of makes sense because we're taking this limit as d tau goes to 0, so already it looks like a sort of derivative basically. The divergence is a scalar derivative that you can get from a vector field. Now, we're going to eventually derive an expression for what div v is, but before we can do that, we need to talk, well, we could do it now, but before we do it, we're going to come up with what is called the divergence theorem, or Gauss's theorem. So, what we do here is we are going to express the flux of V through a closed surface in terms of the volume integral of div V over the volume enclosed by that surface. Enclosed by that surface. This is our task. That's what Gauss's theorem, convergence theorem is about here. We're going to relate the integral over the volume of div V to the flux of V through the surface. And the way we're going to do that is we'll take some arbitrary volume and divide it in two. Okay, so here's some volume, and then I just make another surface inside of it that divides that volume in two.
So S is the whole outer surface I've drawn here. Not the inner surface that I've subdivided with, but S is the whole outer surface. V is the volume enclosed by S. And by drawing another surface inside, then I've broken this up into V1 enclosed by S1 and V2 enclosed by S2. So in other words, S1 now is this surface I've drawn inside plus the portion of the outer surface that has this as its bounding curve. So in other words, the top half is S1, and this bottom portion, this inner surface that I've subdivided the original thing with, and the bottom of the original surface, that's S2, and so the volume has been now broken into two parts, V1 and V2. So V is V1 plus V2, because the volumes add together, basically. Okay, any questions about that, what I'm doing so far? Okay. Now, very important point is that the flux through the original surface, the flux through S, the outer surface of the whole beast here, that is the flux through S1 plus the flux through S2. If I add up the flux through S1 and the flux through S2, that is the total flux through S. And that's because the fluxes through this common surface, common portion of surface that S1 and S2 have in common, are equal and opposite to one another. So because on their shared border, the fluxes of V are equal and opposite. So what am I talking about there? Where am I saying that? Why am I saying that? Well, here's the shared border surface here. Okay, so if I picked a point like this on the outer surface there, which direction would n hat point? Outwards, yep, so it'll point out like this. So this would be n hat at that location, all right? Now, if I'm talking about S1, you know, common border plus the outer portion of the surface on the top here, if I'm talking about S1 and I'm on the common border surface, which way does n hat point, up or down? Points down. So n hat for S1 points down on that common border surface. So if I try to recreate my guy there, kind of like that, n hat for S1 points down, and now shared border surface again, simply drawn again, I've detached it. They're really joined together, but I've detached it for purposes of illustration. Shared border surface, which way does n hat point for S2? On the shared border surface, up or down? Points up in that case. Because for S2, outwards on the shared border system, the surface is up, that's the outside. For S1, it's the other direction.
So when I find the integral over this shared border of v dot n hat dA, the flux of v through that shared border, you're going to get the opposite result for the two surfaces because, for the shared border for the two surfaces, because the n hats are in opposite directions, depending on which surface you're talking about. Does that make sense? Fluxes cancel because the n hats are in opposite directions. The fluxes through the common border cancel. So that means that I can write that the total flux through S of v dot dA is equal to the flux through S1 of v dot dA plus the flux through S2 of v dot dA. Because on the outer surface, I'll get what I want, the flux through the outer surface S. When I'm doing the S1 integral, I'll get the outer surface plus the flux through the common border. And for the lower surface, I'll get the flux through that part of the outer surface plus the flux through the common border surface. But those fluxes through the common border surface cancel each other out, so the total is just going to add up to the flux through the outer surface. That's the crucial thing to understand here, that this is true. So, do I have happiness and joy in that regard, or a lack of happiness? And sadness replacing joy, pouty face. Think of a sad puppy who doesn't understand what's going on. Well, we can keep doing this. We can just go nuts. We can keep subdividing the surface. So I can imagine going, whee, just, oh man, I'm just going to divide this thing like crazy. Break it up into lots of little sub-volumes. Yes. Going crazy on it. Well, what can I say? We can go crazy doing this. Actually, we got upturns at the end because this person is actually kind of maniacally happy about this process. So if F sub SI denotes the flux through surface SI, then we can say that the flux through the whole outer surface there, F sub S, is F through S1 plus F through S2 plus F through S3 plus yada, yada, yada. Or in other words, we just... That's right, yes.
Great.
Yeah. All right.
Can we rewind that and watch it?
Slow motion.
You made the floor dirty.
Yeah.
So concerned.
Yeah.
Yeah, it'd be fun if I have a laser pointer. It's just like lines. I don't know if it would hurt the chip though. Probably not, or probably not. We'll take it.
I was so happy I have. What already?
Or in other words, f through the surface S is the sum over I of f through all the cute little subsurfaces, if you will. And if all the little subvolumes are very small, well then we can use our definition of divergence. We can say that the flux through little surface S of I is the divergence of V inside that surface. And since we're making all the little volumes very, very small, the divergence shouldn't be changing much inside the surface. So we can just say that we can just call it the divergence inside the surface. We're not worrying about the variation from point to point. So since the divergence we define to be the flux divided by the volume, and the limit that the volume gets very small, just turn it around and say the flux is the divergence times the volume, which works if the volume is very small and the surface surrounding it is very small. So d tau I, of course, is just the subvolume I. In other words, the surface enclosed by little s of I. And I don't know why. Oh, I see. Oh, okay, there's a mistake in my notes again there. So that's supposed to be so. So f sub s is approximately the sum of div v times d tau I, not f sub si. Otherwise, I'd be saying the same thing twice there. So the flux through the outer surface, which is the sum of all of the fluxes, will then be the sum of all the div v d taus. Yes?
Hold on. So if x sub si, is that like a straight up equal sign?
Where at?
Right there.
Well, okay, no,
Oh,
it's strictly
we have the
speaking, it's a
function there.
squiggly. Yeah,
I didn't know if
it's
it
really
was-
approximate, yeah. It's really approximate.
Yeah.
Yeah. Well, it does. It's really approximate, so that's fine. Actually, it's better to be a squiggly equal, squig equals something. So therefore, the total flux through the surface, f sub s, of the outer through the outer surface, is approximately the sum of div v times d tau I over all the little subvolumes. And then we do the usual calculus thing. As d tau I goes to 0, as all the little d taus go to 0, and you start to get an infinite number of them, you make these finer and finer subdivisions, so each volume goes to 0 size, but you start getting more and more of them so that their total adds up to the total volume inside the surface. As d tau I goes to 0, the sum becomes an integral. The approximation becomes exact, and the sum becomes an integral, giving us the divergence theorem. Or Gauss's theorem, as opposed to Gauss's law. This is a mathematical theorem, but it gives us another way to state Gauss's law from the one you may be familiar with. Carl Friedrich Gauss, genius, 1777 to 1855. He really was a genius. Which says that the integral over a closed surface of v dot dA, the flux through the surface of a vector field v, is equal to the integral over the volume enclosed by that surface of div v d tau. flux through the surface is the integral of dV d tau. The sum has become an integral, and so we draw a box around this because this is a high holy theorem that we will have many uses for. Well, a big use for, really, is what it comes down to. Okay, any questions?
What is
Yes?
the subscript D?
I'm sorry?
On the second integral, what's the subscript D? Underneath the integral.
Oh, I'm sorry. Yeah, that is the volume enclosed by S. And by that I mean the actual physical volume, you know, in other words, it's not just the number equal to the number of cubic meters, it's the physical volume, the thing that is inside of S. V is the volume enclosed by S. So in other words, I've got this surface in space, and I can find the flux of the vector field V through that surface. I can add up V dot dA at every point on that surface. Or, equivalently, I could find the divergence of V at every point inside the surface and add up the divergence times the volume, all through that interior volume, and you get exactly the same result. Now, this isn't very useful until you can actually calculate what the divergence is. You know, well, okay, there's this thing called the divergence, but how do I find it? You know, if I tell you the vector field V, what's the divergence equal to? Well, happily, you don't sit there drawing tiny little surfaces and calculating their fluxes and then dividing by the volume and taking the limit. There's a nice expression for what the divergence is equal to, and we'll derive what that expression is next time, but just to kind of whet your appetite or to let you see that there is something nice and neat you can do for calculating this divergence. It's not actually hard to do it in Cartesian coordinates. Div V is equal to, anybody remember what it is? Very simple expression.
We don't cross that. Don't cross that.
It's actually del dot V. It's equal to del dot V, or in other words, ddx x hat plus ddy y hat plus ddz z hat. Del cross V is curl V, dotted into v sub x hat plus v sub y hat plus v sub z hat. Well, what do I get if I do that dot product? Yeah, you're just adding up the partials. Yep. You just get dvx dx plus dvy dy plus dvz dz. So it's easy if you got the expression for the vector field, if you know what v is as a function of x, y, and z, calculating the divergence is trivial. You just add up dvx dx plus dvy dy plus dvz dz. A child could do it. A child who knows how to take derivatives. A genius child could do it. So, next time, we'll justify this. We'll show where this expression comes from by actually finding the flux divided by the volume for a tiny little cube surrounding a point in space, and we'll see if this drops out. And voila, that's what the divergence is. Yeah, that's right, yes. And now let's give our speaker a round of applause. Wow. That's pathetic on my part. Anyway, and the good news is the way I'm going to handle it, so there will be homework for next Thursday. And rather than come up with the assignment and give it to you at the start of class today, since I don't know exactly how far I'm going to get, what I'm going to do each Thursday is I'll see how far I got, and then I'll make the homework based on that. So I will post it on the website, starspot.ou.edu/PHYS360. I will also just email it around to everyone. So I'll let you know what the assignment is. So I will see you tomorrow, actually, because you're all going to be at the pizza lunch. And the other thing to do is, I said I was going to, if you got my email, Dr. K's grandmother died, and so I've got a sympathy card, and I'd like everyone to sign it. Where is the card?
I